Welcome back to this new third day on neural networks for architects, and we will talk about numbers and things. And in technical terms, it's about encoding reality with lists of numbers and differences in numbers. We feed then these sets of numbers towards neural networks, and then rationally work with these numbers in neural networks and render it back, these numbers towards reality. This is code called decoder. So we have an encoder, neural networks, decoders. So what neural networks can work with, or the aliens, it's only numbers, a lot of numbers. So therefore we have to put everything towards numbers, to neural networks, bring these numbers back to reality with decoders. So we will talk about that today, how this is done. So let's have a look. We have a list of what numbers can be. Everything can be a number. There's an introduction, a summary of the concepts so far, where to read. Architecture, can go there by yourself. So first, numbers as indexes. For example, with Umberto Eco, there's a book about the infinity of lists. I have the reference here. Numbers can be pages in books, houses and streets, artifacts in museums, and so on and so on. And in technical terms, it's here. So we say data is a list of things. In this case, we have 4 characters. There is this command called part on data. Take a second part in in this extended view, and then in this short form, it's written like that. You can go for the documentation with this menu, and of course here the second part is B, and that's it. So you can have access with this list of indexes. You can access multiple elements of it. They are lists of lists, and you can see that in a tree form, and you can access the third element of the second element, which means the second, third is here, and you get the BC. So this is how lists work and indexes on lists work, and numbers. Characters are calculated with numbers as well. So there are these international standards. Reference is always here. You have to activate the system always with this button here. So for example, if you say have a list of characters, HAY, then with this command, 2-character code, you get the indexes to the ASCII alphabet. So emojis, huge numbers, Chinese characters, huge numbers. The way back, the decoder, just take these numbers from character code, get the numbers, then the characters, or the emoji. That's with indexes on, that's with characters. Words. We will have 2 chapters here. The first is there's a lexicon on tokens. These are 40,000 of them. If you go here, this is always a little tricky with these extensions. So this is the tokens, and then you can say encode here, and then you get the numbers of the words. Indexes to the lexicon, which is the list. So the decoder is just the other way around. So it's a program decoder on tokens. Take the same thing. So for example, this result here, and say decode of this result. It's not working like this. We have to go here. Say what is this? The size. They are 90,200, and then we can use this to decode the numbers to the list of words, of tokens. So that's with indexes to words. And there's another way, which is Indra. Now we take this. This is a neural network which spans a 50-dimensional space where all the words have a point in this space, and corresponding to their usage and their friendships or neighborhoods in 5 billion words in Wikipedia. They got friendships and they got neighborhoods, and it's a kind of multi-dimensional landscape of words. And these are now, and then, for example, you can go here and ask this net model, what is, for example, now tree, the 50-dimensional vector, where is the word tree, or where is the number of the word cat? So the interesting now is that if you have Euclidean distance, so there's a traveling distance between two of these words, between tree and cat, it's 4.5, dog and cat is 1.9, so they are more familiar to each other under the same area in this 50-dimensional space. Dog and house, building and house, tree and house, and so on. So this is not an index. This is a space of numbers and coordinates in a space, the location on a map. So now with colors, there are two different notions of colors. There is, let's go here, there's harmonical of physical view, a harmonical, so it's not harmony, it's harmonical, and a physical view to colors a la Newton, reference here, known as RTF. It's here. Go here, color, red, green, and blue, 100% red, 0 blue, 0 green, 0 blue, then we are at this corner of the cube. That's a color space with 3 dimensions, RGB. So there's another one with goto. So you say HUE, and then this is a physiological. So this is kind of internal view. This is out there. This is how we feel, and we feel about colors, how is the perception of colors, and this is geometrical. This is harmonical geometry. This is geometrical harmony. So it's harmony because it's a unit. So you put the first number here towards the color. This is a rainbow, the circle. The second then is on the brightness, so it's a radius here, and the third is this cone, it's towards the blackness of things. So it's a color, saturation, and blackness. So this is another format, and this is a physiological, and this is called HUE, and CMY is working like that as well. So having that, then we have the prism going to the physical and Newton, having this spectrum. And instead of a prism in bright light, you go in a box and make a slit, and then you are with Goethe and the slit, and then you get this other spectrum. It's the two sides of colors. Very interesting. So the interesting now is, take this, copy this code as a helper function. Then you can go here, for example, with GMI. This is addition for paper. So this is putting colors on top of each other. And this is rendering the 3 circles, and it's adding the colors and CMY. So this is a physiological thing, and this is working on paper. It's reflective. So, and with Grassmann you can go with the addition of RGB colors. The same algorithm here. You can go and try. It's just addition of these numbers. This is CMY color for the 3 circles, and this is RGB color of the circle. So, and taking this, we add that, and then you go with a screen. A pure addition of that, and you go to white. So this is projective. So that's bright light, bright sunlight. It's working like that. Within the reflection, the physiological thing on paper, it's working like that. To be able to do this addition of things on colors, and this arithmetic on colors, this is with Grassmann, and follows the physiological scheme, for example, developed with, shown with Goethe. So this is with colors, numbers and colors. With sensors. So you don't want to just work with color, you want to get with things, abstract things, you just want to take it from reality. So therefore, you have sensors, and there's thousands of them for all physical quantities you can imagine. And it's important that all these sensors, they are much more sensible than our senses. So it's an augmentation of our senses. All these sensors take a physical quantity and translate it to an electric currents. And to get a number of these electrical currents, this is the scheme of that. Let's, for example, say we have the realm, it's working with 2.4 volts. So if you have bright sunlight, it is 2.4 volts. If there's dark night, then it's 0 volt. Let's say it's a kind of middle, so we have 1 point with our sensor delivers 1.2 volt. How to make that a number? So we have a first oscillator. For example, it takes 1 second to go from night, 0 volts, to 2.4 volt, the sun. Now we compare. If this signal here, the voltage of the generator, higher than the signal of the center, of the voltage of the sensor. So this takes 1 second towards 2.4 volts. This is 1.2 volt, so it takes half a second until this thing here switches from 2.4 volts from plus to 0. The same here, this switches, if there is something, it starts switching. So which means if these are equal, so if they are plus both 2.4 volts, this is 2.4 volt. Which means with 1.2 volt here, this stays, and 1 second here, this takes half a second on plus 2.4 volt, and then it falls down to 0 volt. There's another oscillator here. This is a switcher, rectangular oscillator, and this switches, for example, 100 times per second. Which means, again here, if this is both is 2.4 volt, then this is passed. The signal here is passed. Yeah. If so, therefore, this signal here is passed as long within this half second of this. So, and then this is down, which means the switch here is off, which means within half a second, 100 per second, this delivers 50 switches which correlate. So the number of switches, this is counted here, the number 50 now is taken and delivered corresponding to the 1.2 volt. which is middle brightness. So this is called an analog digital converter, and it's everywhere. So and it's super cheap, and it is super fast, and can be super precise. So having that, so we have that. These are very small computers. Raspberry Pi is done for schools. You can have computers for $1 having wireless connection to the internet. This one is for kids. It has a lot of connections for multiple sensors. They all can be calculated, and then they can be delivered to a computer, to a network, and whatever. So, Raspberry Pi, it's made for schools. Mathematica can access these things, look it up, how it is working. So, and if you have a unity of a computer, a network, and a sensor, you can access it worldwide, like for example this weather data of Zurich. That's a weather station in Zurich delivering actual temperature, which should be it's 10 degrees Celsius at this time. So this is things to numbers. Let's go one step further. Numbers and images. How fast it is done and how small it is and how cheap it is you can see it with these photo cameras or video cameras. This is a sensor on a microscope, a small part of it, and with your camera you have millions of sensors in colors, and they all do the job we described here in parallel. And they deliver numbers, an array of numbers, which represents the image. How a camera sensor works is a YouTube. I recommend look it up. So this is how a camera works. Take the picture and get the numbers. For example, this is black and white. And we get the gray values of these pixels. Render it back. This is a decoder to an image, to reality. It's here. Having that in color, then you need three sensors per pixel, red, green, and blue. And then you get more numbers from out a colored picture. Render it back. This is how it is done by code. An LCD LED screen is working like this, having very small lamps, millions of them, running in 100 pictures per second. How it is work, a small YouTube if you are interested. So this is on images. Reliefs, it's just another rendering. This is what we knew from black and white images. It's 4x4 in this case. This is a grid of these numbers. And you just, instead of saying an image, this is here, that's the image of it, black and white image, we simply say, if there's a 1, keep it down. If there's a 4, keep it up. Just another renderer on the same set of data. So each picture instantly can be put into a relief. Or here, with more resolution, get the geodata, geo-elevation around Zurich with 4 kilometers, having 300 by 300 pixels. It's an image of elevation, render that, and we see the Lake of Zurich, the city, and the mountains. We have to calibrate the height of it to make it proper. Or get a picture of it with colors, where the low values are, there's a range, with the low values not white or black, but blue, and the high values goes via green, brown to white, which is called dark terrain as a color function to get this level from 0 to 1, from blue to white. That's on reliefs. Finances, very simple, like this Internet of Things, get the actual financial data, went down, get a range of data from 1st of January up to now. How does it work? On General Electric, finances, numbers, graphs. So numbers can say, you can work on indexes. You say, go from 1 to 2, go from 2 to 3, 3 to 1. So it's a loop, and you can represent it as as this kind of scheme. Or you can represent it as this says, this is element index 1, go to 2, index 2, go to 3, index 3, go to 1. Having it as an image. Go to the floor plan, rooms, make a graph of it, exit goes to V1, V1 goes to V2, to V3, and so on. All this. The rest is just to make it nice looking. This is a graph. You have 2 points of centrality. This is V1 and V6 connected pretty much. If you go here, you see these are the 2 centralities with a lot of connections to rooms, and you see this room here is connected to 2, which is, yeah, you can see it there. Try to read that and decipher it. So it's used like this. Graphs. Graphic, a list of numbers. It's a rendering. You can make an image, you can do, you know, you understand, but there's a certain rendering just to read that as coordinates in a Euclidean space. You get this shape. If you have these graphics, for example, I can show you. Copy. There's the graphics. If we go for then this is a line, and now we have a certain scheme to get the coordinates. We ask for this scheme. We say if there's an x and y, here, 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 then give me that, and then you get the numbers out of a graphics. So graphics is just the rendering on lists of numbers. So next, sound. This is quite interesting because it gives you the complexity of what numbers are about, because they can work in different domains. So very simple here, how to make a sound in geometry. Created geometrical numbers for a sound. So imagine a sound spreads 343 meters a second. So now we go in here with a frequency of 440 hertz. So we have 400. So we fill it with a sine wave 440 times this second, and we put that into 440,000 numbers. So for each of these sine here, we get 100 numbers, which means this is our data. Let's go look it up. Data. This is our data, and you see there are 444,000 of these numbers. So if we look for the first 10 meters, we know these numbers fill a space of 343 meters, so go for 343, do it by 10. So it's Oops. So then we have, this is the data of 34 meters. We filled it up with the sound. So it's a kind of pattern of a sound. So and this is passing by in time. So it's not in space. So it's in time passing by, and this is what you hear. This is passing by. So if you want to hear that, then we say put it in 1 second. That's the sound. So if we put that with 24, then we have 2 seconds, because it's not so fast. Then it's down. Yeah. Here we are. So this is how to fill a space with sounds, a space with sound by numbers. So if you want to have it back, so not these 40,000 numbers. So if you want to look how a sound resonates in a space, you need, so this is a min and max. Then you go with Fourier. And Fourier simply is doing an interesting thing. So now we take, for example, the first 1,000 numbers, and we're looking with Fourier what's coming out, and he says he identifies our frequency. So what he's doing is, he looks at the space, he asks, is there a resonance with frequency 1? Is there a resonance with frequency 2? Is there a resonance with 4, 5, 10, 20, and so on? And it goes to all the frequencies which are there. And then he collects the amplitudes of this resonance and forgets it. And then takes it off the space. And then next frequency, get it off. Next frequency, off, 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 off. So it's a way how to forget what fills the space. And in this case, because we put it here, we filled the space with a single frequency, 440. He just finds the resonance of 440, and therefore it's a single number representing the resonances of a room. And Fourier is just about forgetting geometry and make a ratio for that. So go from geometry to harmony. So if you take now it's like this. So this is how to calibrate it. I don't need it here. So imagine so what is going on here? So if you're at a certain point in this in space, then the numbers passing by in time. So they're passing by, and then you, instead of having a long line over time, you simply fold it and so on. Then you see certain patterns coming up here. But in principle, this is a picture, 1 pixel, 40,000 pixels in width, and I just folded it. So it looks pretty nice if you go with the foldings. Here you see it's a single one, and now I'm folding, and it's getting these interesting effects and images of that, just to get an understanding of frequencies and geometries are. Good. Now, recorded sound. If you got this idea of what a frequency of what is the frequency domain and what is the time domain, or geometry and topology of things, or harmony, now get, for example, this sound. We have this sound. It's a bird. Here we can measure the length and get the amplitudes. It's 80,000 numbers from minus 0.2 to plus 0.2. So we have that. We do the same as we did before. And here you see, if we make a picture of the sound passing by, it makes no sense. There's nothing you can see of the sound. But now if you go with the frequencies, so which means forgetting and getting all the frequencies and measuring the references, however, which color you look to the space, and forgetting the red, forgetting the, so which is a certain color, the red, or orange, or green, and so on, look what remains. So they all are there in parallel, in time. So time is always abstracting, orthogonal to space. There's no speciality in there. So it's passing by like this, and you see all these colors coming by of space. And this is how forgetting, this is a harmonic place. So if we now look how this works, so for example, if we make this spectrum, it's called a spectrum of the first 100 numbers. This is the intensity of the frequencies, like we have it here. We make an absolute, so we don't distinguish whether it's plus or minus. Certain intensity, we can put it here as well. Absolute of this, and then we have this. Put that to this image. And of course, this 100 here is a very short time. We don't fill the second with the 80,000, so it's 100th of this bird. And if we put that together over time, we get a kind of image of these sounds where we can start to see the bird singing. Let's have a sound here. That's a bird, it's here. You see, this is an harmonic picture of frequencies. So this is called a spectrogram here, and this is how neural networks work on sounds like images. So you need this transfer. So images are always in geometry, sounds are in harmony, and you need Fourier to get it forth and back and forth, and you have to be very clear what you want to do. You've seen that in audio, if you make a picture of that, makes no sense. If you now this is the last one here. If you take a picture and make directly an audio of this, it's coming. It's always very fragile in internet. You have to copy it. The whole thing, you always have to copy it to your desktop. So then you hear the sound. simply makes no sense. So this is the domain of the visual. This is this here is the domain of the auditive. Yeah, this is the domain of the auditive. You can hear it. It's working pretty well. And if you transfer it, it's in most cases makes no sense. This makes no sense. These crazy sounds here makes no sense. This makes sense. And then you need these kind of complicated calculations to transfer it and to treat sounds like images, because this is towards rationality and differences of numbers. You don't have differences of numbers in the frequency domain, which is of reality, measuring the reality. These are numbers not working in neural networks. So you have to be very sharp with these things. That's for this chapter. Thanks for watching, and seeing you with a little more complex formats and discussion of that.